Presented by Caltech.
Okay, so our next speaker is Professor Shanhui Fan, who's a professor of electrical engineering and the director of the Edward L. Ginston Laboratory at Stanford. His research interests are in nanophotonics. He's published over 350 referee journal articles and given over 270 invited talks, granted 53 U.S. patents. Professor Fan received an NSF Career Award, David and Lucille Packard Fellowship, National Academy of Sciences Award for Initiative in Research, and the Adolph Lamm Medal from the Optical Society of America. He's a fellow of APS, OSA, SPIE, and IEEE, and today he's going to talk about control of thermal radiation using photonic structures for energy applications.
Oh, thank you for the introduction. It's good to be here. I like to talk about using photonic structure to control thermal radiation. As a way of motivation, if you look up in the sky, you will see two very prominent thermodynamic resources, the sun, of course, and also away from the sun, the outer space, which is very cold at 3 Kelvin. Now, from a basic thermodynamic point of view, something that's cold is very important as well. So this is a center on light-matter interaction. The manipulation of light is very important for harvesting the thermodynamic resource because light actually provides remote wireless access to it. We all know that about the sun, and that's why we work on the solar cell sitting on Earth. Somewhat less well known is the fact that we also have radiative access to the cold sink as well. So in this talk, I'm going to talk about 3 works that are related to this interplay of manipulating both sunlight and thermal radiation to trying to simultaneously harvest both the sun and the coldness of the universe. And, but the background here really is that we have radiative access to the outer space. The black curve here shows is the transmission spectrum of an atmosphere. And I like to draw your attention to the wavelength range between 8 to 13 micron, where the atmosphere is fairly transparent. And that happened to coincide with the peak of a 300 Kelvin blackbody. The point here is that a 300 Kelvin blackbody, if given sky access, will be able to radiate heat out into outer space. And that, in fact, is what every one of us do. Every one of us does every single day when there's a clear day and you walk outside. You're actually radiating heat out. And so as a result, it's not too surprising to imagine this as a cooling mechanism. And this actually had been done for at least 4 decades. The typical experiment that people have done is to take a black emitter surrounded by insulating material, bring this to a roof at night and have it face the sky. It's actually a fairly straightforward experiment. You can try that fairly simply to show that you can cool to a temperature that's about 10 to 15 degrees Celsius below ambient at night by these kind of simple experiment. Now, doing this at daytime, on the other hand, would be more interesting because daytime is hotter as far as cooling is concerned. And also, it's a bit more challenging. So the point that you would like to do during the daytime, if you want to do radiated cooling, is you now have the sun as well. So you need have a broadband control of light-matter interaction. And in this case, that involves reflecting all the sunlight while radiating the heat out in the 8 to 13 micron. So what you would like is an emissivity spectrum that look on the right, the red curve here, where you have unity emissivity spectrum in 8 to 13 micron and reflect all the sunlight, so have 0 emissivity or no absorptivity in the visible and near infrared. And that's something that we set out to construct. So on the left here is the picture of the sample with which is a very good mirror. So you see myself, you see Ashwath and Lin Xiao, 2 of the primary people in this work. And it's an 8-inch silicon wafer. And it behaves basically like a very, very good mirror. And on the right is the cross-section view of the structure. This is made out of 7 dielectric layers deposited on a silver mirror that's deposited on silicon. The dielectrics are made of hafnium oxide and silicon dioxide. The top 3 layers here have thickness of hundreds of nanometer, and these are responsible for thermal radiation. Silicon dioxide has what's called a phonon pluriton. Basically means that the silicon and the oxygen atom at room temperature will vibrate against each other. And since they are partially charged, this vibration is optically active. It radiates thermal radiation, and that's the thermal radiation that we're trying to use. The bottom 4 layers here, again made of hafnium oxide and silicon dioxide, have thicknesses on the order of tens of nanometer. And these, together with the silver, is designed to give a very good solar reflectivity. So on the left here is the solar, is the spectrum of the structure in the solar wavelength window, that you have basically very little absorptivity over the entire wavelength range, roughly from 0.4 to 2.5 microns, so over almost the entire solar spectral window. On the right is the structure spectrum in the thermal wavelength side, and you see a very large emissivity peak in the 8 to 13 micron, and that gives you the thermal emission. So this actually gives you the required spectral response. If you put this thing on a roof, and this is what we did, so you see on the left the picture of the setup on the roof of our electrical engineering building. And you can test the structure. Now, the key here, because the roof is very hot, is to be able to set up the experiment actually just right. And there are a few important aspects. We use the low-density polyethylene as the opening of the apparatus in order to cut down convection, because we're trying to reach below ambient air temperature. The sample is also placed in a transparent box to make sure that nothing in contact with the sample is heated up by the sun. So with this setup, now this is the main data. So the green curve here is the solar irradiance on the sample. We tilt the sample to face the sun to test the worst case scenario, and you get about 800 watt per meter square of sunlight hitting the sample. The black curve is the ambient air temperature, and the blue curve is the temperature of our sample. And what you see is a 5 Celsius difference between the radiative cooler and the ambient air temperature. So this actually spontaneously reach a temperature that's below ambient air temperature by 5 degrees Celsius when it's given sky access. So what we demonstrate here is a proof of principle is that you can actually make structure that under sunlight can actually cool by itself without using any electricity. And we are very interested in scaling this up towards actual air conditioning system. And this is a artistic rendition of how the system would look like. And this is something that we're actually building. The point to keep in mind is probably that this in many ways look like a typical solar thermal system. What we have are these panels with water pipe underneath it so that we can cool down water to below air ambient temperature, and then we can deliver that into a building. And that's almost like a solar thermal heater running in reverse. On the other hand, in this case, what we are doing is to basically not use the sunlight at all, so we're reflecting all the sunlight. It would be, on the other hand, quite interesting to combine the concept of radiative cooling with sunlight utilization. And as a simple example, air conditioning actually play a very major role in the gas mileage of a car underneath the sun. Now, from our experiment, of course, if you like to reduce a car temperature under the sun, the simplest way is to make it look like a mirror, which is fine, but many people probably would prefer a car that have slightly different color. So the point here is that you really would like to have a mechanism to combine radiative cooling, because you are facing the sun in the sky, with the utilization of sunlight. More closer to what we work about in the center, in the second part of my talk, I'm going to talk about solar cell cooling. Solar cell cooling is actually quite important in practice. Silicon solar cell on the rooftop scenario operates actually at a temperature much higher than the ambient air temperature. The typical operating temperature is about 50 to 55 degrees Celsius. This actually has very severe penalty on both the efficiency and the cost of the solar cell. the 20 degrees Celsius increase will give you about 2 percentage point drop in solar cell efficiency, which of course is enormous in the context of practical application of solar cell. It also cut down the lifetime of solar cell by a factor of 2. And so it influenced the cost as well. What would be nice is a mechanism to passively cool down solar cell without using any energy. Now, of course, solar cell sits on the roof and therefore have sky access. So it would be very nice if one can combine the absorption of sunlight in this case with the capability for radiative cooling. If you take a piece of silicon by itself, and on the right is the absorptivity spectrum, it of course has strong absorption in the solar wavelength side, but it has relatively weak absorption in the 8 to 13 micron window or in the thermal wavelength range. So a silicon by itself actually is a relatively weak thermal radiator. And therefore, it doesn't do that much radiative cooling by itself. So what one would like to do in this case, in order to do radiative cooling, is to imagine that you can put a layer on top of silicon. Now, this layer need to be transparent because you are trying to do a solar cell here. So this layer cannot affect the solar absorptivity of silicon. But on the other hand, what you like to do is very significantly enhance the thermal emissivity in the longer wavelength side to get the heat out. And so what we do here is we try to do a experimental demonstration of this idea of putting something on top of a solar absorber in order to achieve radiative cooling of absorber. So in our experiment, we consider we compare 3 different structures. In the first structure, we have a silicon wafer, 525 micron thick silicon, with a 75 nanometer silicon nitride layer. Silicon nitride here is typically used in solar cell for anti-reflection. So this is actually a wafer that's usually the starting wafer for people to fabricate solar cells on. And to compare to this bare silicon structure, we compare it with 2 different samples. One of them, we simply put 500 micron thick silica on top of the silicon structure. And in the second one, we take the 500 micron silica structure and then put a silica photonic crystal into it. So we basically etch holes into this 500 micron thick silica. And on the top right corner here, you see the SEM image of the structure. The periodicity here is about 6 micron because we're trying to control thermal radiation, which has a longer wavelengths. So these are micron scale periodicity. And so this actually was made out of photolithography. So these 3 structures have its spectral response shown here. On the left here is the solar spectra, the solar absorptivity spectrum of the 3 structures. They are dominated by silicon, so you absorb very strongly once you go above silicon band gap. And you can see the absorptivity of the 3 structures are actually very similar to each other. In fact, the photonic crystal sample have about a few % higher in total solar absorption because the presence of the hole has a mild light trapping effect for light inside the silicon layer. But in general, their solar absorption behavior are roughly the same. On the thermal side, on the other hand, their behaviors are very different. The black curve here is the silicon structure. As indicated in the beginning, it doesn't have that much thermal emissivity absorptivity. The blue curve here is the absorptivity of silica by itself. You see that indeed it has strong emissivity or absorptivity. However, the silicon oxygen phonon platon, which is responsible for thermal radiation, also is responsible for an enhancement of the refractive index. As a result, there is a very large impedance mismatch between air and silica in this wavelength range. And that gives you a pronounced dip in the emissivity right inside the transparency window, which is undesirable actually for thermal radiation for cooling purposes. In comparison to these 2, the red curve here is the thermal emissivity of the photonic crystal sample. what you see is that the introduction of the holes actually give you near unity emissivity over a wide range of wavelengths, all the way from about 6 to about 20 micron. And this comes about because the holes actually provide a gradual impedance matching mechanism between the air and the silica. So consequently, what we have in the photonic crystal sample is actually a visibly transparent but near ideal blackbody. This is a somewhat unusual notion, I guess. It shouldn't be a major surprise, but if you read a textbook, your typical mental image of a blackbody would not be visibly transparent. So it's somewhat unusual. We then put it on the roof again and for the test. And we did 2 tests. In the first test, what we do is the same setup as we did in the radiative cooling experiment that I show you, that we put this in a box, and then the box is covered by transparent polyethylene film to cut down convection. In this case, the green curve, again, is the solar irradiance that's hitting the sample, so it's getting to be about more than 900 watt per meter squared that day. The black line is the bare silicon structure, has a temperature of about 70 to 80 degrees Celsius. Both the planar silica and the photonic crystal sample has a temperature that's much lower. The photonic crystal has a temperature that's about 13 degrees Celsius below the bare silicon structure. And also, this occurred in spite of the fact that the photonic crystal structure actually has a higher solar absorption among all 3 samples. In this case, is about 30 to 40 watt per meter squared more compared with both the planar silica sample and the bare sample. So this shows you that one really can see very significant cooling in the solar absorber structure. In this particular demonstration, we have the polyethylene film covering the entrance to the box for the purpose of cutting down convection and getting clean data. These structures under sunlight, because they're absorbing, actually have temperature that are higher than the ambient air temperature. So in this case, convection is actually a cooling mechanism that you can use. So if you take out the polyethylene cover, then you can combine the radiative to convective cooling. And this is an experiment when the polyethylene cover is taken out. You can see the temperature now is a lot lower. It now fluctuates, and it also fluctuates a lot more because the convection and the wind now give very large temperature fluctuation in these structures. Nevertheless, the photonic crystal sample still has a temperature that's consistently lower by both the bare sample, compared with the bare sample and the planar silica sample. And the average temperature difference is about 5 degrees Celsius. So what we show here is one can really reduce a solar absorber, which has the same absorptivity as a solar cell, by a temperature on the order of 5 to 10 degrees Celsius. This actually would translate into about a 0.5 percentage point to 1 percentage point improvement in efficiency by open circuit voltage enhancement. And that's something that we are trying to demonstrate at the moment. So, but it does point out that it's actually quite interesting to combine the concept of radiative cooling with the possibility of sunlight utilization. So, in the very last half of my last part of my talk, I'd like to switch gear a little bit and talk about a concept that we call negative illumination. As a way of a background, now that we have a structure that has its temperature that can fall below ambient simply by radiative cooling, it's very natural then to imagine that you can get some electrical power out of it. As a theoretical concept, of course, you can run a Carnot engine between an ambient, let's say at 300 Kelvin, and the blackbody radiator facing the universe at 3 Kelvin, therefore has a temperature below 300 Kelvin. And you can run a Carnot engine of it to get power out of it. And you can work out the theoretical number of what the optimum is, and it turned out the optimum work you can get is about 48 watt per meter squared if you put a Carnot engine between the ambient blackbody radiator. there's nothing wrong about the theoretical concept. In practice, you can imagine a thermoelectric cooler putting in between the ambient and blackbody radiator. On the other hand, what I like to show here is a concept that's slightly different, which is perhaps a more direct way to get electricity out of the possibility of radiative cooling. And we know that if you have a photodiode facing the sun, which is hotter, there is a net photon flux from the sun to the photodiode, and therefore you can get electricity out of this. We call this positive illumination because that's where the sunlight hitting the diode. Now, what I like to show here is that the opposite process can also give you electric power. In this case, you imagine a diode maintained at ambient air temperature, for example, facing again the sky, but the diode sits on the hot side. In this case, there's a net photon flux coming out of the diode, so we call it negative illumination. What I like to show you is that in this case, you can also extract electric power out of it as well. So in many ways, this will be a way that's extracting power out of the sink, but in a form that will look almost like a solar cell. The physics of it actually can be understood from the Shockley-Queisser analysis. The black curve here is the typical IV curve of a diode when it's surrounded by ambient at the same temperature. In this case, the IV curve passed through the origin of this curve with I equal to 0 and V equal to 0 being passing through that point, and there's no electric power generation. In a typical photovoltaic mode, you have a hot object, and consequently, the diode develop a positive open circuit voltage, and the IV curve shift downward into the red curve here, and that's how a typical solar cell operates. On the other hand, if the object is cold, the IV curve will shift upward. In this case, you will actually get a negative open circuit voltage, and again, you could extract power out of it. And so in both positive and negative illumination, you can generate power. No one, surprisingly, have done an experiment to explicitly show this, so we decided to do an experiment. In this case, we take a MCT photodiode facing a temperature-controlled emissive surface, and to demonstrate the physics, we put a chopper in between with a blade that's rotating around. So the chopper has a temperature that's at ambient air. Consequently, when the blade blocks the view, the diode sees the ambient, and when there's no blade that blocks the view, the diode sees the emissive surface. So as the chopper rotates, if you recall the photocurrent, it will look something like this when the diode is facing the hot surface. You can correlate this curve by the position of the blade, and when the diode sees the chopper blade, that sets the 0 of the photocurrent, because the diode is at equilibrium. And then when diode sees the hot surface, you see a negative current, as you expect from the Shockley-Queisser analysis. Now, in this case, it's consistent with the fact that the IV curve shifts downward. If you face a cold surface, on the other hand, you can see the curve flip. In this case, you see a positive current when the diode is seeing a cold surface. So this confirms what we have talked about from the Shockley-Queisser. And if you superimpose these curves together, you basically see this distinctive flip of the sign of the photocurrent, which is an indication that we're extracting current in both cases, but with opposite sign. And you could actually generate power, in this case, for both positive and negative illumination, as we've seen in this experiment, and that fits actually very well with the theory. So one thing that will be interesting is to talk about the theoretical limit of it. As I mentioned, if you put a Carnot engine on the left here, you get a maximum power of 48 watt per meter squared. As it turned out, the scheme on the right have a higher power density limit compared with what's on the left. What's on the left, in spite of the use of Carnot engine, actually is not the thermodynamic limit. So what we have here, in fact, is something that theoretically can reach 54 watt per meter square, and also in a different control of thermal emissivity can reach Carnot efficiency limit in its efficiency. So with that, let me briefly summarize. I'd like to acknowledge my students and postdocs who have done the work. The First two parts are mostly Ashwash Rama and Lin Xiaozhu, and the last part was done by Parthes and Sanon, who is sitting there. And also thank you for your attention.
Does anyone have any questions?
Thank you for this talk. The cooling of the solar cells is so important. So let me mention another mechanism for cooling the solar cell. And that is, it happened actually by accident at Alta Devices. They were not trying to cool the solar cell. They were simply trying to break the world record. So they put a very good reflector on the back of the solar cell in order to allow the luminescence to be trapped internally, and that was the key toward breaking the record voltage and efficiency of a solar cell. But when they sent it out to be tested at NREL, they monitored, they do official testing, they monitor the temperature, and they say, oh, there's something wrong with our instrument, and because the solar cell is much colder than expected. And the reason the solar cell was colder is that it had a reflector. The reflector was not meant to cool the solar cell, it was just meant to trap the internal luminescence, but it also had the effect of reflecting all those infrared rays that were useless to the solar cell. And so it also ran cool. Now it seems to me you can combine the effect that you're talking about, you can combine it with a good reflector on the back of the solar cell and get even a greater temperature drop.
Yeah, that's a very interesting idea. I think that in the silicon cell case, of course, the luminescence is fairly weak. So, but I think for high efficiency cells like gallium arsenide cell, this could be very interesting.
No, I'm not saying it to break the record in the silicon cell. The motivation was to break the record, but now the key point is that you have a good mirror. Mm-hmm. If you have a good mirror at the back of your solar cell, you get cooling because you don't allow the infrared rays to heat up the solar cell. So you have now two cooling mechanisms. You have your mechanism, and you have the fact that the infrared rays are being reflected back into space.
Sure, yeah.
Is the traditional encapsulant glass on a typical photovoltaic module seeing some of this benefit, or is there not enough thermal contact between encapsulant glass and a cell to actually get the benefit?
I think it would do some. The question which we are trying to figure out is how much does it actually do? There are two aspects of it. As we've shown in this experiment, a flat silica structure is not ideal for radiative cooling purposes. Also, the thermal contact, as you pointed out, is very important. For example, the effect of cooling would decrease fairly substantially if you increase the thickness of silica to about a few millimeters. Because the thermal modeling is basically that the cooling occurred at the top surface.
Thank you, Sean. It's a great talk. Yeah, my question was closely related to that one, so you partly answered it already. I was going to ask if you had modeled the thermal impedance with the photonic crystal, and then specifically, if you knew the temperature offset between the crystal and the cell, yeah. And which were you measuring in your recent publication? Which temperature?
Right. So we actually have modeled let me say in this way, in the Optica paper, and you can check it out, we actually did a model of it. The unknown of the model is how well the contact of the cell to the silica is. In this case, we just use a standard thermal impedance of the silicon-silica interface, but actual cell, of course, doesn't look like that, and that impedance could actually be far worse. In other words, if one do it right, the potential is actually could be actually a lot higher.
So, Shanhui, thanks again for the talk. For either the radiative cooler or the solar cell cooler, also the angular distribution matters, right?
Yeah.
And ideally, you'd like to have something that's an ideal emitter emitting into as large a solid angle as possible. Did you, in your measurements, have emission only in a narrow solid angle, or what is the range of solid angles? And also, maybe you can comment on the effective field of view that you see from the atmosphere. For example,
Right.
At oblique incidence, the atmosphere itself is thicker
Right.
as well, right?
So our structure is actually fairly omnidirectional. In the paper, in the PNAS paper that's going to come out, we actually have an angular measurement of the sample. And the emissivity for the photonic crystal sample barely change to about 60 to 70 degree angle of incidence. So it's fairly flat. This gives rise to the question of what exactly is the optimum. If there's no atmosphere, then of course an omnidirectional emitter is the optimum. In the case of as you pointed out, that is thicker, the atmosphere, you should tailor the emissivity based on the transmission coefficient of the atmosphere. So you would expect there's a threshold below which, so there's an angle of incidence above which you want the emissivity to go to 0. Because at that point, the atmosphere is no longer a net contributor of cooling. But that's not what we have done. We actually done an omnidirectional kind of emitter.
So if you took this idea and tried to extend it a little bit, let's say you could use some quantum dots to absorb all the sunlight and re-emit it and capture all of that sunlight, no concentration factors or anything like that, you would get the heat generated in the quantum dots and then essentially a low heat version of the light going to the solar cell. Would you get a similar kind of temperature improvement by putting all of the heat, say, on the top surface from those photons?
As long as there's no heat conduction pathway. So what Paul has talked about actually is very interesting in that respect, because his quantum dot is on the other side of the light pipe that's presumably very far from the solar cell. Yeah, I think that could be quite interesting. In a planar configuration, though, if you put directly on top, you still have to worry about the thermal contact. So then that's less obvious.
The question about the polyethylene window that you used.
Yeah.
Did you find that it was also absorbing of infrared light?
It turned out to be fairly transparent. What we use is about 12.5 micron thick polyethylene. These are actually just the standard kitchen wraps, so that everybody has it. I think it's above 90% in the
8 to 13
yeah,
micron
8 to 13,
window.
I think it's above 90%. In fact, it's an interesting question of whether we can use a harder and thicker polyethylene to get high transmission. And if you know a way to do it, let us know.
Just a quick question to clarify, when you mentioned the loss from heating your silicon cell, was that a absolute loss or relative efficiency loss?
So I quote a number which is from the literature, that's relative, so 0.45% of the efficiency. So that translates into about, I think, 10 degree will give you roughly half a percentage point for 20% cell.
Thank you.